The ingenious design of the aluminum beverage can. The can begins as this disc called a blank, punched from an aluminum sheet about 3/10 of a millimeter thick. The first step starts with a drawing die, on which sits the blank and then a blank holder that rests on top. We'll look at a slice of the die so we can see what's happening. A cylindrical punch presses down on the die, forming the blank into a cup. This process is called drawing. This cup is about 88 millimeters in diameter, larger than the final can, so it's redrawn. That process starts with this wide cup and uses another cylindrical punch and a redrawing die. The punch presses the cup through the redrawing die and transforms it into a cup with a narrower diameter, which is a bit taller. This redrawn cup is now the final diameter of the can, 65 millimeters, but it's not yet tall enough. A punch pushes this redrawn cup through an ironing ring. The cup stays the same diameter as it becomes taller and the walls thinner. If we watch this process again up close, you see the initial thick wall and then the thinner wall after it's ironed. Ironing occurs in 3 stages, each progressively making the walls thinner and the can taller. After the cup is ironed, the dome on the bottom is formed. This requires a convex doming tool and a punch with a matching concave indentation. As the punch presses the cup downward into the doming tool, the cup bottom then deforms into a dome. That dome reduces the amount of metal needed to manufacture the can. The dome bottom uses less material than if the bottom were flat. A dome is an arch revolved around its center. The curvature of the arch distributes some of the vertical load into horizontal forces, allowing a dome to withstand greater pressure than a flat beam. On the dome, you might notice 2 large numbers. These debossed numbers are engraved on the doming tool. The first number signifies the production line in the factory, and the second number signifies the body maker number. The body maker is the machine that performs the redrawing, ironing, and doming processes. These numbers help troubleshoot production problems in the factory. In that factory, the manufacturing of a can takes place at a tremendous rate. These last 3 steps, redrawing, ironing, and doming, all happen in one continuous stroke and in only a 1/7 of a second. The punch moves at a maximum velocity of 11 meters per second and experiences a maximum acceleration of 45 Gs. This process runs continuously for 6 months, or around 100 million cycles before the machine needs servicing. Now, if you look closely at the top of the can body, you see that the edges are wavy and uneven. These irregularities occur during the forming. To get a nice, even edge, about 6 millimeters is trimmed off of the top. With an even top, the can can now be sealed. But before that sealing occurs, a colorful design is printed on the outside. The term of art in the industry is decoration. The inside also gets a treatment. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a metallic taste and also keeps acids in the beverage from dissolving the aluminum. The next step forms the can's neck, the part of the can body that tapers inward. This necking requires 11 stages. The forming starts with a straight-walled can. The top is brought slightly inward, and then this is repeated further up the can wall until the final diameter is reached. The change in neck size at each stage is so subtle that you can barely tell a difference between one stage and the next. Each one of these stages works by inserting an inner die into the can body, then pushing an outer die, called the necking sleeve, around the outside. The necking sleeve retracts, the inner die retracts, and the can moves to the next stage. The necking is drawn out over many different stages to prevent wrinkling or pleating of the thin aluminum. Since the 1960s, the diameter of the can end has become smaller by 6 millimeters, from 60 millimeters to 54 millimeters today. This seems a tiny amount, but the aluminum can industry produces over 100 billion cans a year, so that 6 millimeter reduction saves at least 90 million kilograms of aluminum annually. That amount would form a solid cube of aluminum 32 meters on a side. Compare that to a 787 Dreamliner with a 60-meter wingspan. Now, after the neck has been formed, the top is flanged. That is, it flares out slightly and allows the end to be secured to the body, which brings us to the next brilliant design feature, the double seam. On older steel cans, manufacturers welded or soldered on the ends. This often contaminated the can's contents. In contrast, today's cans use a hygienic double seam, which can also be made faster. This can is cut in half so you can see the cross-section of the double seam. To create this seam, a machine uses two basic operations. The first curls the end of the can cover around the flange of the can body. The second operation presses the folds of the metal together to form an airtight seal. While the operations themselves are simple, they require high precision. Parts misaligned by a small fraction of a millimeter cause the seam to fail. In addition to the clamping of the end and can body, a sealing compound ensures that no gas escapes through the double seam. The compound is applied as a liquid, then hardens to form a gasket. The end, attached immediately after the can is filled, traps gases inside the can to create pressures of about 30 psi or 2 times atmospheric pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, nitrogen is added. So why is a beverage can pressurized? Because the internal pressure creates a strong can despite its thin walls. Squeeze a closed, pressurized can, it barely gives. Then, squeeze an empty can. It flexes easily. The can walls are thin, only 75 microns thick, and they're flimsy. But the internal pressure of a sealed can pushes outwards equally and so keeps the wall in tension. This tension is key. The thin wall acts like a chain. In compression, it has no strength, but in tension, it's very strong. The internal pressure strengthens the cans so that they can be safely stacked. A pressurized can easily supports the weight of an average human adult. It also adds enough strength so that the can doesn't need the corrugations like in this unpressurized steel food can. While initially pressurized to about 2 atmospheres, a can may experience up to 4 atmospheres of internal pressure in its lifetime due to elevated temperatures, and so the can is designed to withstand up to 6 atmospheres or 90 psi before the dome or the end will buckle. Why is there a tab on the end of the can? It seems a silly question. How else would you open it? But originally, cans didn't have tabs. Very early steel cans were called flat tops for pretty obvious reasons. You use a special opener to puncture a hole to drink from and a hole to vent. In the 1960s, the pull tab was invented so that no opener was needed. The tab worked like this. You lift up this ring to vent the can and pull the tab to create the opening. Easy enough, but now you've got this loose tab. The cans ask you to please don't litter, but sadly these pull tabs got tossed on the ground where the sharp edges of the tabs cut the bare feet of beachgoers or they harmed wildlife. So the beverage can industry responded by inventing the modern stay-on tab. This little tab involved clever engineering. The tab starts as a second-class lever. This is like a wheelbarrow because the tip of the tab is the fulcrum and the rivet the load. The effort is being applied on the end. But here's the genius part. The moment the can vents, the tab switches to a first-class lever, which is like a seesaw, where the load is now at the tip and the fulcrum is the rivet. You can see clearly how the tab, when working as a wheelbarrow, lifts the rivet. In fact, part of the reason this clever design works is because the pressure inside the can helps to force the rivet up, which in turn depresses the outer edge of the top until it vents the can, and then the tab changes to a seesaw lever. Looking from the inside of the can, you can see how the tab first opens near the rivet. If you try to simply force the scored metal section into the can using the tab as a first-class lever with the rivet as the fulcrum throughout, you'd be fighting the pressure inside the can. The tab would be enormous and expensive.
Novelis is the world's largest recycler of used beverage cans. They arrive at its factory in Warrington, England from all over the world, compressed into bales, each weighing up to 1,000 kilograms and containing as many as 65,000 aluminium cans. The bales of compressed cans are loaded onto a conveyor and fed into a 340 horsepower shredder. Aluminium is tricky to sort because, unlike some metals, it can't be separated out with a magnet. So next, the shredded scrap passes through an optical sorter at a rate of 3 meters per second. The machine uses infrared sensors to sort out what's metal and what isn't. Then blasts away any plastic or glass with jets of air. A powerful magnet sucks up any scraps of steel, leaving just aluminium. The next problem is aluminium doesn't melt until 660 degrees. The paint and lacquer aren't so lucky. They're instantly vaporized. the clean aluminium chips are ready for the next stage, melting. Two furnaces hit a blistering 730 degrees and handle up to 100 tons of aluminium each. The trouble is, when the aluminium melts, it reacts with air, forming a layer of aluminium oxide that floats on top. This unwanted oxide is known as dross. A brave furnace operator skims it off with a giant steel spatula. And the alloy is ready for the casting area. The only problem is getting there. A river of molten metal flows downhill to a holding furnace that's the size of a double-decker bus. Somehow, they need to pour the liquid metal into a mould. Remarkably, the solution is to tip the entire furnace. And a fountain of deadly metal pours into one of 3 moulds set 10 metres into the ground. Inside, they will be cast into 3 towering blocks of aluminium. After 2.5 hours, they have 3 giant aluminium monoliths, called ingots. Each one is 10 metres long, weighs 27 tonnes, and is made up of 1.5 million recycled cans. Today, demand for aluminium is so high, the ingots don't lie around. Their transformation back into cans starts with a 900-kilometre journey to a rolling mill in Germany. Here, they're heated in another furnace to 525 degrees. This relaxes the bonds between the aluminium atoms, releasing any stresses within the ingot. Then it's passed back and forth through a series of rollers. It's a bit like rolling pastry. Each set of rollers thins out the metal until it's 1/4 millimetre thick and 10,000 metres long. That's 1,000 times its original length. Massive reels of the aluminium arrive back in the UK at Ball Packaging to undergo reconversion into cans. They produce around 6.5 million cans here every day and send them all over the world. That's a whole lot of aluminium. Luckily, there's plenty more where these came from.